All right, so here we go. So here's our problem. We're going to try to find all the bar forces. There's 1, 2, 3 of them. And we're probably going to first need to find our reactions. Now, we could be quite successful by just going to B and trying to write joint equations at B. We have 2 unknowns, 2 equations. We could get that, but we would run out of information as we came down here. So the first thing I'm going to do is find the reactions for that free body. So let me just quickly kind of redraw, not to scale, a system. And this is a 60 kilonewton force. And I'm going to assume at the pin A that I have a force in the X and Y directions, and then at C another force. So I want to find those reactions. So what should I do first? I can sum moments at A, I can sum forces in the X direction. Both of those will give me one equation and one unknown. I can't sum forces in the Y first. So I'll start with the moment. So I'll indicate that I'm doing right-hand rule and that we'll sum moments at A, and we're going to assume it's an equilibrium. So starting with CY, that creates a positive moment, and the moment arm is 5 meters. And then I have a negative moment created by the 60 kilonewton force, and it has a moment arm of 10 meters. So it looks like CY is positive, and it's equal to 120. That seem reasonable? So next, I'll come along, and we'll assume up is positive, and I'll sum forces in the Y direction. Make sure that's an equilibrium. So I have AY plus CY, and then I have the 60 kilonewton force acting down. So I can solve for AY, and AY looks like it's negative 60. So let's check it. Does it make sense that AY is actually acting down here? Yeah, I think so. If you think of C as like the pivot point of a big seesaw, if you push down on one end, you better push down on the other end to keep it balanced. That seems reasonable. And then we'll finish it up by summing forces in the X direction. I'll assume to the right is positive, and all I have, it seems, is AX. So that means AX is 0. Any questions about that?
Are there no reactions at B?
B, it's all internal. So there are no reactions at B. Now there will be now, because that's the first part of the problem. So let me draw a line here. And now I want to find the internal forces, right? So what are the axial forces? So let's apply our strategy. Is there a bad choice? Should we choose A, C, or B? Well, I think all qualify, because if you look at each joint, there's only 2 unknowns. We can write 2 equations. But there's probably better choices than others. What about B? Is this a good place to start? I say no. Because you're probably going to think in your head, traditional XY coordinate system, if you look at these 2 forces, each force is going to have an X and a Y component. And it's going to be a little nasty keeping up with it. However, if you drop down here and look at A and C, and you have a traditional X coordinate system, you can see AC only X, and then your other terms have X and Y. So I think those will be better to deal with. Even though if you've made a mistake at A and C down here, that information will propagate into your solution. Can't help that, but I think you'll be better off there. So just to do them in alphabetical order, I'm going to start with A. So I'm going to go to joint A. Okay, get ready. This is going to take me a while, so give me a second. I'm going to draw my free body diagram for A. Everybody get that? There it is. Make sure you use a straight edge. Right? It's a point. Okay, it's a bad joke, I know. All right, so I'm now going to apply the forces I have at A. So I come over here and I see, AX is 0. Great. AY is negative 60. I assumed Y was up, so that means it's down. Okay? Then I'm going to assume tension force in AC and tension in section AB. Now, what is this slope? Well, it looks like it has a rise of 5 to a run of 10. So that's really a 1 to 2 slope. You're going to need that to calculate the component. Now, what should I do first? Should I sum forces in the X or sum forces in the Y? Well, if I sum forces in the X, I'll get one equation in 1, 2 unknowns. So I need to sum forces in the Y. So we'll assume up is positive, and I'll sum forces in the Y direction. What do I have in the Y direction? Well, I've got the Y component of AB. So if I have a 1 to 2, what would be the hypotenuse? Square root of 5. 2 squared plus 1 squared. So the vertical component will be 1 over the square root of 5. Force AB. If you don't like that, then you would take the arctangent of 1 over 2 and get an angle, and then take the sine of the angle. And you would get 1 over the square root of 5. So since I don't want to do that up here, I'm just going to say it's, well, I'm not going to say, I'm going to calculate that it's 1 over the square root of 5. Everybody see that? So what would the X component be? 2 over the square root of 5. So that's acting up, and then I have minus 60 kilonewtons acting down. So one equation, one unknown. I can solve for the force in AB. It looks like it's going to be positive, and whatever 60 times the square root of 5 is. Somebody do that for me. 132, I'm guessing.
134.
Oh, pretty good guess. 134 point something, Mr. Gargas?
0.16.
That's close enough. Let's say 0.2. Positive number means compression or tension? Tension. So now that I have AB, what can I do? Some forces in the X direction. So what do I have in the X direction? Well, I have the force AC plus 2 times the square root of 5, the force in AB. So I should be able to solve for AC. Well, AB is positive. I put it in here as positive, so it looks like AC is going to be negative. And that should give me, I'm thinking it's 120. But I'm guessing.
Right.
I guess it's a good guess. All right, let's stop and think about this right now. So let's look back at our element here. Does it make sense that AB is in tension?
Yes.
Yeah, I think if you think of this being held down and you pull this, AB is probably going to stretch. It's not going to contract. At the same time, what's going to happen to AC? Well, this whole bottom core is going to want to push in. So I think AC being in compression seems reasonable. So what do you think BC is going to be? compression. So now that you know that, or you have a good insight, make sure that works out when you go to the next place. And speaking of which, what's the best place to go? B or C? I would still run away from B. That's some funky geometry up there. So I'm going to go to C. Why? Well, in my standard XY coordinate system, only BC has a Y component. So now I go to joint C. I'm going to do this joke one more time because I like it. I'm going to draw my free body diagram as C. Get ready. All right, there it is. All right, I won't do any more. Okay, so what's happening on that? I got CY, and CY was 120, and it was positive, so that's going up. And I have a tension force in AC, and I have a tension force in BC. What's the slope of BC? What's the rise over run of this?
1:1.
Yes, 1:1, 5:5.
I thought we established that FAC was in depression.
I don't care. I always assume
Tension.
tension. When I actually use the equation, what value am I going to plug in for AC? Whatever I calculated, which happens to be compression, or a negative value. Now let me ask you this. Can I find BC without including AC? How? Some forces in the Y direction. Excellent. Let's do that. So if I sum forces in the Y direction, what do I get? Well, what is the Y component of BC? Well, if you have a 1:1, the hypotenuse is square root of 2. So it'll be 1 over the square root of 2 times BC. That's the Y component, and that's going up. Also acting up is my 120 kilonewton force. So what is the force in BC? Looks like it's negative. Good. We thought it was going to be compression. So what's 120 times the square root of 2? Something like 168?
169.7.
169.7? And we're done. Now, if you've got lots of time and resources, what would you do next just to make sure? You would sum forces in the X direction, and you could solve for AC. And you better get, if you don't, there's an error somewhere. Another way to do it would be to put your negative 120 in here and your new value for BC and make sure it is in equilibrium. So there's a way to check when you get to this point. Okay? Any questions about this problem? All right, then I'll stop it.